Hello, welcome. On behalf of AMTA, American Membrane Technology Association, and Toray Membrane USA, I'd like to welcome you to today's webinar on hot sanitizable RO membranes. My name is Sue Guibert. I'll be moderating the webinar today, and a bit about myself. I started working at a company called Xenon Environmental in 1996, and some of the work I did in R&D was testing Toray's hot sanitizable elements. So a bit of full circle. Anyway, we ended up getting 3 patents using Toray's hot sanitizable elements, and the whole purpose of this little story is to say Toray's membranes have been in use for a very long time, almost over 30 years. And then, of course, the company actually moved towards hollow fiber membranes and deviated away from ultra pure water. But I ended up joining Toray as their UF MBR tech support person in 2009. So anyway, our webinar today is hosted by AMTA and Toray Membrane USA. Ben Weaver will be presenting. And after the presentation, there'll be a question and answer period. So I will go through some housekeeping items now. If you can see on the slide, you're all muted. However, if you would like to head out and switch from your computer to your phone, you can use the control panel located in the upper right corner of your screen. Select telephone in the audio panel, and then the dial-in information will be there. Also, you can submit questions anytime during the presentation, which we can discuss at the end of Ben's presentation. You just need to select questions from the drop-down menu towards the bottom of the control panel. Also, you can download today's presentations by clicking Handout in your control panel and saving the PDF to your computer. Lastly, at the end of the presentation, there'll be a survey, and if you have time, we'd appreciate it if you could fill that out. So I'd like to introduce Ben. We at Toray were very lucky to get Ben last year, hired Ben. He's been working in the membrane industry for over 15 years in a variety of positions, applications, operations, and sales. He joined us as a product line manager for our specialty elements, which includes hot sanitizable elements, which he'll be discussing today. He can help solve separation challenges, food, beverage, and pharma industries. And today, again, he'll talk about our hot sanitizable elements and how it can be added to your toolbox to develop separation solutions to meet client requirements and optimize process economics. So with no further ado, I will hand this over to Ben. Thanks very much for joining.
Great, thanks, Sue. Give me a second here. I'm going to make sure I get the right screens here. And 1 second. You see, hey, Sue, can you confirm which screen? Is it the notes or the presentation?
Yeah, could you maybe put it on presenter? I see the screen and the presenter notes as well. There you go.
How about that? Perfect. Great.
Perfect. Yep.
Uh-oh. Sorry about that. All right. Well, welcome everyone, and thank you for joining today's session. We'll take a deep dive into heat sanitizable RO membranes, and we'll go over some different applications, how they're used in applications, and then we'll finalize with a case study. And we'll have time at the end for Q&A. As Sue mentioned, please type the question into the chat box, and we'll go over as many questions as we can at the end of the presentation. Let me grab. Sorry, my GoToWebinar is hiding my advanced button on the slideshow, so give me 1 second. There we go. All right. So as we go through this webinar, we'll start with introductions. We'll go into some standard RO background, just some basics on the technology. We'll go through how that differs from heat sanitizable RO membranes, what makes them heat sanitizable and what do we have to do to make them heat sanitizable. And then we'll go through the sanitization process and how it's done, because it is very important to make sure we maintain the longevity of the element, and that sanitization process is very critical in that process. And then we'll go through a number of applications where heat sanitizable RO membranes have been deployed. And then finally, we'll go through a case study in a dairy heat sanitizable RO application. So as Sue mentioned, Toray has been making membrane products for a very long time, and we offer products in a wide range of membrane configurations and cutoffs, starting with the most open on the right in the microfiltration and MBR. We have hollow fiber ultrafiltration for drinking water, pretreatment to RO for seawater desalination. Offer nanofiltration elements as well for softening and partial demineralization. And then also RO, which is Toray's bread and butter, and what we've been involved with for decades in the water treatment area. So we also offer specialty separation membranes, as Sue mentioned, and those are used in food, beverage, pharma applications. And the heat sanitizable RO is really in this area where we're combining the strength of Toray RO membranes along with the configurations in specialty designs such as sanitary and heat sanitizable applications. So as we were take a step back and really, what is osmosis and reverse osmosis? And so osmosis is the spontaneous movement of water across a semi-permeable membrane in an area from low solute concentration to an area of higher solute concentration. The process aims to balance concentrations on both sides of the membrane. In biological systems, osmosis helps plants' roots absorb water, helps regulate water levels in cells and tissues. And really, the semi-permeable membrane allows water to pass to block larger molecules such as salts, and creating a pressure known as osmotic pressure. This principle is also the foundation for reverse osmosis. So where external pressure forces exceed the osmotic pressure to reverse the osmotic pressure or osmotic process, where that way we can create very clean water and remove salts from a highly concentrated salt solution and purify that even further by messing with the pressure gradient and exceeding the osmotic pressure to create reverse osmosis. So what really helps drive that is the reverse osmosis membrane. And the reverse osmosis membrane is a 3-layer membrane based on a polyester support layer, which in this graphic is shown here. We also have an SEM photograph on the left here. And so this is going to be your polyester support layer. And that's the foundation of the polysulfone layer. That is the support layer of the polyamide thin layer. So these 3 layers really constitute the RO membrane, with the polyamide really doing the most of the rejection principles of the RO membrane. So feed water will come through this way. The molecules such as salts will be retained on the surface, and product water will go through the membrane and collected in the permeate carrier and into the product water tube of the element. So this RO membrane is really the foundation of the separation properties, and really which is the first critical part of the heat sanitizable RO element. Without the proper RO membrane, you really struggle creating the right properties in a heat sanitizable RO element. So heat sanitizable RO membranes can be used in beverage water applications, but primarily they're historically been used in pharmaceutical, medical, and biotechnology applications, where either regulatory requirements or very high pure water requirements require the use of heat sanitization as part of the process to meet either required regulatory requirements or water quality as part of the process. We are looking in areas where microbiological is concerned and areas where chemical sanitation doesn't necessarily perform as well as what we need it to do. And this can be due to chemical contamination, extra flushing, and there's several areas where thermal sanitization can be advantageous to chemical sanitization. So how does the heat sanitizable RO membrane compare to standard RO membranes? First, we look at the temperature tolerance. If you look at a standard RO membrane, typically the max temperature is about 45 degrees C in applications. And if you start to exceed that in a standard RO membrane, you may start to degrade the membrane itself, or you may start to swell the polysulfone layer, which yields a decrease in flow and can show poor performance due to that exposure to increased temperature. Where heat sanitizable RO membranes can be sanitized up to 85 degrees C. Now, when you do the heat sanitation initially, you will see a slight drop in flow and a slight increase in rejection, but it is not insurmountable. It's very minimal change in properties due to the construction durability of the RO membrane. When it comes to cleaning options, the heat sanitizable RO membrane opens up the avenue to more flexible cleaning regimes. So with standard RO membranes, you're limited to chemical cleaning with pretty generic chemicals. There are some more proprietary chemicals out there to improve that performance. But with being able to introduce heat-based sanitization with heat sanitizable RO membranes allows for more flexibility in that process, and it allows potentially to replace some chemistry to save money on that aspect as well. When it comes to applications, we'll go into more on the applications in subsequent slides, but typically standard RO membranes are used for drinking water, general industrial use, wastewater, where heat sanitizable RO are used in more either regulated or high performance applications in the food and beverage, biotech, and pharmaceutical area. Usually these heat sanitizable RO membranes are touching more high value materials, and so provide a higher benefit from a value perspective from the separation process. So that goes into cost. Standard RO membranes are going to be lower initial costs. If you look at a price per element, it's going to be a lower cost because it is more of a commoditized element. Where heat sanitizable, because of the value that they produce and are able to withstand higher temperatures and typically have longer longevity, they will have a higher initial cost. But if you take into account the entire total cost of operation, it becomes more interesting from a process economics point of view to utilize heat sanitizable RO membranes in several applications. And in any application where you have biofouling issues, heat sanitizable RO membranes may be a good option to use. Biofouling resistance in standard RO membranes is moderate. There is some technology out there to help minimize that, but being able to utilize heat to sanitize that allows for a higher capability of biofouling resistance with the heat sanitizable RO membrane. And this leads to a lifespan where if biofouling is severe, you will have shorter life on a standard RO membrane where you can extend the life using heat sanitizable RO membranes. So what makes this element and membrane heat sanitizable? And first and foremost, the membrane is critical. We talked about the 3 layers and how they're impacted a little bit by the heat conditioning. Well, the membrane that is used in the heat sanitizable membranes are very predictable when they are exposed to heat. And what that means is that before and after heat sanitization, you are going to have a predictable performance before and after. And we'll go into what that looks like later on in the presentation. Next is robust chemistry with high durability. We are hitting these with heat and thermal and high temperatures. And so we want to make sure that the chemistry is robust and designed to handle those heat sanitization cycles. In addition, the membrane is the key component there to withstand, but it's not the only component of the membrane that is needed to be modified in order to make something heat sanitizable. There are several other components that we'll go into here. So when you look at the spiral wound RO element construction, there's several pieces. So you have your feed spacer here. You've got your membrane, which is doing the separation as well. Once the water goes through the membrane, you're going to have your permeate carrier or permeate spacer here, which collects the permeate water, spirals it around to the permeate tube where it can be exited out and permeate. And so when we're looking at what is really impacted and what needs to change in this element, we're looking at a few different components here. So the membrane is one. The feed spacer needs to be modified, and we need to look at proprietary components to make sure that it is not impacted with heat sanitization processes. The permeate spacer, that needs to be ensure that we can handle the thermal properties in addition to the pressures that it is under in operation. And then finally, we want to make sure that the adhesive holds up under the temperatures as well. So we talked about the feed spacer in particular, and here's a couple of different images. The feed spacer is basically a mesh net that is put in between the membrane layers to create a feed channel of the RO membrane. And so the feed water will traverse across this mesh, and it is specially designed to ensure that we are creating disruption in the flow, and that will make sure that the foulants are not building up on the membrane surface, but they are allowed to stay in solution and be removed from the element. Same is true with standard RO and heat sanitizable RO. However, we need to ensure that when the element is hit with temperature, it doesn't degrade quickly, and we end up with an issue like we see in the picture on the right, where that feed spacer starts to extrude completely out of the element, and that leads to performance issues. You can see this picture here shows the focal point of it, the feed spacer. And you can see here, this is a normal strand where this strand has been chemically degraded a little bit. And so when you have that degradation, you start to lose performance and potentially have that feed spacer slip out of the element, which damages the membrane and can cause performance issues. So once again, this is the first, outside the membrane, this is one of the major components that we need to ensure that is designed to handle the thermal temperatures and then the high temperatures that we'll see during the heat sanitization. The next is the trico or permeate carrier. So this sits below on the permeate side of the membrane, so against the polyester of the RO membrane. And really it is designed to ensure that we are guiding the permeate water through the element so it can be collected in the permeate tube with as little back pressure as possible. We want to ensure that there's no resistance once the water gets through the membrane to be collected into the permeate tube. And in cases where you have heat sanitization, you may impact those flow channels because most of these materials are made of plastics. They are going to be impacted by thermal changes. And if you change that temperature too quickly, you can impact how those plastics are held together and the form factor of those components. And the permeate spacer is designed to withstand high pressure of RO applications, but we also have to make sure it can withstand the high temperature along with the high pressure in heat sanitizable applications. When you can combine the membrane leaf or the membrane and the permeate spacer, this really and the feed spacer, that makes up a membrane leaf. So the last aspect that we'll talk about when it comes to materials is the adhesive. So we want to make sure that the adhesive can withstand the temperatures that will be seen. And so we want to make sure that any adhesive that is used to seal off the permeate carrier from the feed material will ensure that will hold up to the high temperatures. So the permeate tube is pretty much the same. We may have to use different materials due to different regulatory requirements, but really it's the membrane, the feed spacer, the permeate carrier, and then the adhesive that we have to ensure that can hold up to the high temperatures. So as we look back at the element construction, we can see that there's a number of opportunities for places where heat sanitization can impact the construction. So making sure that we have the right materials is critical. The last part I'll discuss here is the difference between an FRP, a fiberglass reinforced plastic wrap, or a cage wrap, which makes it a sanitary design. So we do offer heat sanitizable RO elements in both FRP and cage wrap. Now you may be asking yourself, what would cause us to use one or the other? So this is a typical FRP wrapped element, which may look like a standard water RO element. So some of the differences between the standard RO element and the FRP and the heat sanitizable and an FRP configuration is going to be the components used on the permeate side of the element. So in applications where the permeate water is, the product of interest, and that would be for like water for injection in pharma applications, or in other, pharmaceutical or healthcare applications, where the regulatory is really concerned on the permeate water side. So we can use, components that are FDA compliant on the permeate water side with FRP wrapped elements to provide a regulatory certification in certain applications. This element here is a sanitary or a cage wrapped element. And what that allows you to do is that allows you to sanitize, chemically sanitize on all sides of the membrane, but it also allows for FDA compliance of all materials, both on the concentrate side and the product side of the water. And so in certain cases where we're looking at concentration applications in beverage industries or dairy industries, this is where the cage wrapped element being able to be FDA compliant on both the concentrate and the product side is advantageous, because in some cases the concentrate is our product. And so if we look at this as what is our product of interest, and is it really the concentrate water or is it the permeate water, can help guide us in what element configuration we want to use for our application. Another consideration between FRP and cage wrapped elements is bypass. So the top diagram is similar, to a standard water RO, where you have a brine seal that is forcing all the feed water through the element itself to create that disruption to ensure that the feed flow and the foulant is not building up on the membrane surface. So you can see, in a standard 8-inch element, we're probably at 3 cubic meters per hour from a feed flow or brine flow point of view. Where with cage wrapped elements, you make a brine seal. And so if you have water going on both sides of the element, you have to consider the bypass in order to really make these operate in a similar manner. So when you consider the bypass, you are going to have a certain amount of flow that goes around the outside of the element. And so you almost have to double the flow in order to maintain that cross flow velocity on the membrane surface. So when we're talking about heat sanitizable RO, there's some benefits here, because with FRP elements, if you try to do chemical sanitization, it's going to be hard to ensure that you're getting this area completely sanitized with chemistry. So while you have that issue with chemistry, you don't have that issue with thermal, where the temperature can traverse through the FRP and heat up the area both inside and outside the element. And so you can do more enhanced sanitization using heat rather than chemicals with the FRP element. With a cage element, you can do the sanitization both ways, but there are some advantages from a thermal perspective as well when it comes to contamination of products. In a lot of the cases where we want to make sure that we have no product contamination from chemistry, we want to make sure that we're using cage wrapped elements so that we can make sure that they're flushed completely and there is no chance for contamination. So when we talk about heat sanitization, I want to take a step back and ensure what it's not. And sanitization is not sterilization or disinfection. So we're not creating a sterile environment or anything like that with heat. But what we are doing is we're controlling the microbiological activity in the system. And so, typically sanitization can be done by either thermal or chemical means. And we saw on the last slide, what are some of the advantages of thermal versus chemical, being able to traverse through different materials where heat can go through the FRP wrap. Chemistry may not be able to get through all items like that. And then depending on the system, the sanitization procedure should reduce the viable organism population by about 50 to 99%. And once again, not disinfection, sterilization. This is really just microbiological control in the water system. So when we look at chemical sanitization versus thermal sanitization, so with RO membranes, we can't use very many oxidants because we will degrade the membrane very, very quickly and really make it irreversibly damaged. Now, in a lot of cases, hydrogen peroxide can be used with RO membranes, but there is still a risk that in the presence of heavy metals such as iron or manganese, you can create irreversible damage to the thin film composite membrane. And you also still have the risk of having chemistry residue in the system itself. And so when you go turn it back onto production systems, you do risk the chance of having chemical contamination in the products themselves. And so being able to focus, chemical sanitization can do a good job of sanitization, but there are certain things that you have to be aware of. And then after sanitization, if you want to try to either preserve the system, you have to make sure that it's completely flushed out before introducing sodium bisulfate, which is a oxygen scavenger to ensure that microbiological activity can't grow once it's been sanitized. So there's a couple different means of chemical sanitization, but most of them require oxidants that can be damaging to the membrane or potential for contamination when we start the process back up and are back into production. Thermal sanitization can be pretty simple. There's a couple different options to do it. So the first is to introduce heat exchanger into the feed system so that we can heat up the water and then run it through a recirculation process. And this is typically for 30 minutes. We'll go up to about 80 to 85 degrees C, and we'll do this at very low pressure. I'll go into the details of how we do that sanitization in a couple slides. Another option that we have is to use the standard CIP type system, where we have a CIP tank, and we can use that to heat up the water to our temperature of 80 to 85 degrees C, and then once again introduce that to the system and allow that to recirculate for about 30 minutes as we do our heat sanitization process. So here is a typical diagram of the heat sanitization process. And I mentioned that we want to be careful when we're doing this because these still are plastic components, and we don't want to increase the rate of temperature very quickly, as we can have some thermal changes and potential either adhesive issues or potential the feed spacer issues. So we want to make sure that we're ramping up the temperature very slowly. And then we also want to ensure our max TMP is only 25 psi. So we're doing this at low pressure in the process as well. So just want to make sure heat sanitization is just a sanitization process. These aren't high temperature RO membranes designed to operate at 80 degrees C. We only do the 80 degrees C when we're doing the sanitization process at these low pressure and low delta pressure conditions. And so when we do the first heat cycle, we will have a drop in flow and an increase in rejection. And this is really critical for the heat sanitization process because some RO membranes are built a little bit different, where that change in flow and that change in rejection is much more dramatic than with the Toray products. So when we look at heat conditioning, most elements, heat sanitizable elements, require heat conditioning right out of the box. And that is to ensure that, we talked about the predictable nature of the membrane after heat conditioning. And we want to make sure that the end result is meeting the requirements of the application. And so a lot of the competitor elements will start at 97% sodium chloride rejection and then build up to over 99% after that heat conditioning. With the Toray product, you can actually use the membrane right out of the box. And typically it's going to have at least 98.5 or 99% rejection of sodium chloride. And then the flow is going to be somewhere between 12 and 13,000 gallons per day. right out of the box. And so you can use that as an advantage to have lower energy costs. And if it meets the permeate requirements, you don't necessarily need to heat condition right away. You can get a little bit of runtime on them and then heat condition them. And at that time, the flow will drop a little bit and the rejection will increase to the higher levels shown in the spec sheet. So our spec sheets are designed to show the flow rates and rejection after heat conditioning, but even out of the box, they are a high performance membrane. We also offer both heat conditioned and non-heat conditioned elements. So we can do that in our factory. So if we have a client that is looking for a preconditioned RO membrane, we can do that in the factory, and that saves a step on site if that's it provides value to the client. So some of the advantages are both heat conditioned and non-heat conditioned that we can offer. And really, you don't necessarily need to heat condition right out of the box on the standard non-heat conditioned membrane. So as we look at some of the applications that these heat sanitizable membranes are used in, you'll see a lot of higher value applications: pharmaceutical, biotech, personal care cosmetics, dialysis, food and beverage processing, bottled water industries, and the dairy industry. So a lot of the times we are looking at higher value in either regulatory requirements or other things that demand heat sanitizable RO membranes. So in the pharmaceutical and biotech world, heat sanitizable RO membranes are used for water for injection and then purified water systems in these processes. And why these are used is because we need high microbial control. And heat sanitization is a regulatory requirement in many cases. And so, some of the benefits here is being able to have the thermal sanitization to meet the regulatory requirements without having the membrane damage, while still meeting that stringent conductivity and TOC requirements. I mean, we're in this case, we're talking, water for injection. We're talking water going into the body. We need to ensure that it is, very high quality water and has no, issues with contamination or anything like that. So the rejection characteristics of the membrane are very, very critical. And being able to minimize the risk of biofouling and contamination is very critical in these applications as well. In addition, with the long service life, with less chemistry involved, we have fewer changeouts and less downtime in systems. In the personal care and cosmetics world, going into my daughter's bathrooms and you see their creams and lotions and all their cosmetic products, and a lot of times the number one ingredient is purified water, and so this water we need to have high purity water to ensure that when they make these formulations for personal care products, that they are consistent and that we want to make sure that there's no microbiological activity to prevent spoilage and protect consumer safety. So being able to heat sanitize up to 85 degrees eliminates that microbial risk in the membrane system. And then that high salt and organics rejections make sure that we have product consistency and maintain the prevention of contamination in the system. And then being able to sanitize with heat as opposed to chemistry allows for sensitive formulations and even clean labeled products to ensure that we aren't using any type of chemistry for potential contamination. And then with the sanitary systems, with the sanitary elements, they can meet good manufacturing practices of hygienic engineering, and in some cases can meet FDA and EU compliance for that. Another application is in healthcare and dialysis centers. So once again, we have water purification for dialysis or sterile applications. And really the reason behind that is for patient safety demands. I mean, we're talking once again, from dialysis where blood is being treated and then being put back into the body. We want to ensure that there is no potential for contamination and really just from a safety point of view. So once again, heat sanitization can minimize the microbial contamination. The ultra pure water reduces the risk of pyrogenic reactions or infections for insensitive patient applications. And it meets standards for dialysis water, and so meets some of the standards that are required for that. And then in cases where frequent sanitization cycles are required, these elements are designed to go through those heat sanitization cycles and still provide high performance and long life. So in the food and beverage processing area, this is where we see, a little bit more uptick in heat sanitizable RO membranes, where historically standard RO membranes have been used, but because of either higher demands for quality or to minimize the use of chemistry, we have seen an uptick in food and beverage processing. And this can be used in ingredient water production, product concentration, and even water reuse and recovery. And some of the main things for this is to prevent biofouling again, but also to comply with food safety standards. And in a lot of cases, we're concentrating products. And so being able to have those food safety standards and being able to sanitize without chemistry allows for a lot of flexibility in the cleaning process and to ensure hygienic design to avoid contamination. So once again, these are heat disinfection can protect against microorganisms without chemicals. We still have that high performance and long membrane life. So in the bottled water industry, once again, standard RO membranes have been used predominantly, but we are seeing an uptick in heat sanitizable, especially outside the US, in international areas. And one of this is because we want to standardize, a lot of companies want to standardize their product and making sure that they're delivering clean, neutral tasting water. Whether that water is done in Europe, or in Asia or in the US, bottled water companies have a brand. And so they want to make sure they maintain that brand integrity by creating a very consistent product. And heat sanitizable RO membranes have been able to be used to help maintain that product consistency. In addition, being able to heat sanitize allows for the maintenance of hygienic conditions, and it's suitable for 24/7 operations in high output facilities. So for some of the previous applications are going to be lower volume and smaller systems, but heat sanitizable RO membranes can be used, in large volume, high output facilities just as easily as it can be used in smaller systems as well. And in some cases, there are FDA compliance that are needed in some of these applications. So there are ways to meet the regulatory demands in these applications. So finally, the last application we'll talk about is in the dairy industry, where heat sanitizable membranes are being used more often in certain applications, such as whey concentration, lactose concentration, water for diafiltration, and water recycling. And you can appreciate in the dairy industry where milk is really the baseline of a lot of these applications, there's a high risk of bacterial contamination. So being able to have the option for heat sanitization to meet the hygiene requirements allows for, once again, elimination of a potential chemical contamination, which if we're talking in, for whey or lactose can be problematic. The temperature can be beneficial there. Risk of contamination, we're eliminating pathogens without chemicals that can taint the products and cause, whether it's lower yields, but really, we want to make sure that the final product integrity is there. And we can meet the regulatory compliance that a lot of these applications require, whether that's 3A sanitary or FDA compliance. And these elements are designed to handle very frequent cleaning cycles. So as opposed to, maybe some of the standard water applications in pharma or bottled water, where you may be only cleaning once every several weeks or several months, in this case, elements are being cleaned almost every day. And so being able to handle those cleaning cycles is really important. And I'll take a second here to tell a story of one of our clients in Europe who switched from a standard RO membrane to a heat sanitizable RO membrane in a dairy. It was a whey concentration application. And what they saw was, because of the frequent cleaning cycles with chemistry, that was really the cause of the membrane to fail. And so because we're cleaning so frequently, they saw an opportunity that, hey, if we can eliminate the sanitization step, and use heat sanitization instead, we may be able to prolong the life of the membrane and really improve the operation. And so what they did is they started testing side by side a heat sanitizable membrane to their standard RO sanitary membrane. And what they saw was they were getting about 12 to 13 months life on the standard RO membrane. When they started introducing the heat sanitizable RO membrane into their process, they were able to extend that life to about 18 to 19 months. So almost a 50% increase in membrane life. And for really a minimal cost increase. When you compare sanitary element price to a heat sanitizable RO membrane price, there's not a huge differentiator there. And so being able to extend the membrane life by 50% was a huge win for that client. We see this a lot more in Europe, where Europe is moving away from chemistry and doing more, I'd say, green processes where they can use heat in order to sanitize. But the benefit is you're not degrading the membrane as much during your CIP process, which leads to longer membrane life. So one other case study I'd like to go over is when we were using our RO membranes to demineralize NF permeate for diafiltration water at a whey production plant. So in this case, a leading producer of whey ingredients was struggling to keep their bacteria counts in the RO permeate. And that RO permeate was used to diafilter the water to enhance the yield of the whey the whey ingredients. And so as we're introducing bacteria into the diafiltration system, you can see that the RO permeate goes right back to the NF to help improve the yields there. So if we have bacteria in this loop, that can cause a lot of issues with fouling and really shorten up the membrane life there. And so really they wanted to find a better way to keep the bacteria counts down in the permeate and to allow this process to last longer. And so what they did is they did an evaluation where they installed the heat sanitizable RO elements side by side with the standard RO elements. And their goals was to look at flow rates, because they wanted to maintain the flow rates that they were achieving now. They didn't want to reduce anything, but they wanted to increase their organic rejection to ensure that we weren't having any bacteria in the permeate water. And so what the results were, after several weeks of operation, we could see that the heat sanitizable elements outperform the existing RO levels. And it was both when you're looking at COD rejection, in addition to looking at the flow rates as well. So in the table on the left, you can see, the summary of it, where COD was very, much lower, about 80% lower than the existing RO membrane, and the flow rate was about 50% higher than the existing RO. And so, we always joke around in membrane companies, clients are always looking for higher flow, higher rejection, and usually there's a trade-off between one or the other. Well, in this case, we were able to achieve higher flow and higher rejection using the heat sanitizable RO membrane. So we do offer design projections using our heat sanitizable RO membrane. So if there is any questions on how we want to design these systems, we can definitely provide assistance on that. There are some minor nuances when it comes to designing because of the bypass flows. And so the bypass flows do create a little bit of a challenge to make sure that the design is accurate, but we are able to use the software and use our expertise to design the system properly using heat sanitizable RO membranes. So as we're wrapping up here, a few things that separates Toray heat sanitizable membrane is that we do 100% factory wet test our elements. I did mention earlier that we do offer both heat conditioned and unconditioned available. So a lot of times these systems, when they install the systems, they'll do a CIP and a heat conditioning. However, we do offer the option to use the elements right out of the box if the regulatory demands the system don't require a CIP or a heat sanitization to begin with. So we do offer both there. The advantages there is you can have a little bit higher flow if the permeate quality is met. And so you can lower your energy requirements for the first part of the operation of the system. And then, the differentiator with the Toray RO is you have a less pronounced performance change when heat conditioned. So when you heat condition, you are going to decrease the flow a little bit, increase the rejection, but being able to minimize that difference in performance and be able to predict what that will be after the heat conditioning is what's very important there. So in conclusion, there's a number of opportunities for heat sanitizable RO membranes. Historically, they've been used in the pharma applications, in biotech, and in cosmetics. But there are some advantages now from standard RO applications where heat sanitizable RO membranes are being implemented more and more. And that would be in the beverage area, bottled water area, and in the dairy and food and dairy industry as well. So I appreciate everyone's time joining. We'll have some time for questions and answers here, and really appreciate you joining us today.
Hi, thank you very much, Ben. Yeah, so we're now going to begin our Q&A portion of the webinar. So thank you all for submitting your questions. As a reminder, you can still submit questions through the question panel in your attendee control panel. So first question is, why are drinking water RO membranes not heat sanitizable?
So yeah, a couple different reasons. So first, a lot of times it doesn't require the heat sanitization in drinking water applications. You'll have pre-treatment ahead that is taking care of the organics, and typically that can be like a Toray hollow fiber ultrafiltration membrane. But a lot of times, you're taking care of the organics before. In addition, there can be degradation of the membrane if you try to heat sanitize a standard RO membrane for drinking water. The membrane will swell, and you could provide some damage to the polyamide layer, and so that's why you'll see some performance degradation. But really, it comes down to the requirements of the application. For drinking water, just don't really require the heat sanitization that the HS membranes can do.
Great. Okay, so is the membrane actually different with heat sanitizable membranes versus brackish or seawater RO elements?
Yes, it is different. So as mentioned, if you would try to heat treat or heat sanitize a standard RO membrane, it wouldn't perform nearly as well. That change in performance, whether it's a decrease in flow, increase in rejection, would change the membrane drastically. Where the heat sanitizable RO membrane is really designed to handle that heat with minimal changes to performance.
Right. Okay. Next question is Trico, is that the same thing as a permeate spacer?
Yeah, so I kind of said Trico and permeate carrier and permeate spacer kind of synonymously. I kind of relate Trico back to Kleenex. Kleenex is a tissue, but it's a brand name, and Trico is actually the weave that's created on that. So the Trico weave really creates dedicated channels for the permeate water to traverse through the permeate carrier with minimal back pressure. And that Trico weave is what creates those channels. But permeate carrier, permeate spacer, Trico are all similar things. So we're all referring to the same material there.
Okay. Can heat sanitizable membranes be used in water reuse projects?
Yeah, absolutely. I mean, it will come down to process economics, but in cases where there's severe biofouling in water reuse applications, it's going to provide a very, very good quality water. And actually, that the case study that I did for the lactose demineralization is really kind of a water reuse application where we're recovering the water to reuse somewhere else in the process, and creating diafiltration water in order to do that. So it absolutely can be used in water reuse applications, and especially beneficial in cases where biofouling is a major concern.
Yeah, we did do a pilot study with our hollow fiber UF in Ventura treating wastewater, and we did sanitize. There was, I'm just going by memory, but I will. There was heat involved in cleaning the membrane, the process stream before it hit the UF membrane. But I don't know of any reuse applications where the RO is heat sanitized, but I think it would be, usually it's a chloramine residual that's kept through the UF and the RO, but again, chloramines would degrade over time. So heat sanitization is actually an interesting idea to use in reuse applications. Last question is, where are your heat sanitizable membranes made? And yeah, you mentioned FRP wrapped and cage wrapped. Yeah.
Yeah. So Toray is a global company. So we have global operations. The heat sanitizable sanitary elements are made in the US. So they are made in Poway, California, at our factory. And then we also offer, so the cage wrapped elements are all made in the US. The FRP elements, we have options that are made here in the US, but we also have options that are made in Japan, depending on where you are located in the world and where it makes sense to receive those membranes from. So very similar. They perform the same way, but we do have options to buy domestically or buy overseas as well.
Okay, thank you, Ben, for attending. Thanks everyone also for attending. So in just a moment, the survey will be displayed. So if you have time and you can offer your feedback, that would be greatly appreciated. On behalf of AMTA, Toray Membrane USA, thank you for joining and have a great day.
Thanks, Ron.
Thanks. Also,